Welcome to AI Peer Review. We dig into the latest papers, pull out the key insights, basically save you the reading so you can get straight to the core ideas.
And today, we're tackling a really persistent challenge in generative AI. It's about getting beyond just, slapping sound onto video. We're talking true cinematic audio-visual generation.
Exactly, because for ages, especially in open source, you were kind of stuck. You had these multi-stage things, right? Text to video first.
Then maybe an audio-to-video step.
Then maybe you run something else, try and fix the lip sync or align the sound effects. It felt, well, a bit hacky.
A lot of heuristics involved, yeah. Or you look at the big players, like Google's VO3, amazing stuff, but totally closed off, leaves the rest of the research world playing catch-up.
But that might be changing with OVI. This paper proposes something quite different, a unified paradigm.
Right. They're essentially saying, forget treating audio and video as separate streams you merge later. OVI thinks of them as one single generative process.
A one-pass generator, from noise straight to, hopefully, coherent AV.
That's the goal.
Okay, so our mission for this deep dive. Let's unpack how OVI actually works. How do they get this movie-grade sync they talk about? We need to look at the twin architecture, this temporal scaling thing, and the training strategy. Apparently no specific sync loss needed?
Exactly. It's quite clever. So where should we start? Maybe the architecture itself. How is it different from, say, older attempts like Universe 1? Those often struggled with the fusion part.
Yeah, let's start there. The big buzzword seems to be symmetry. OVI uses an 11 billion parameter symmetric twin backbone.
And symmetric here isn't just a loose term. It means they are architecturally identical copies, one for video, one for audio.
Right. Same number of transformer blocks, 30 of them. Same attention heads, 24. Same model dimension, 3072. Everything matches.
And this symmetry is really the enabler for the core technical piece, blockwise, bidirectional, cross-modal attention.
Okay, break that down. Blockwise and bidirectional.
It means that within every single one of those 30 transformer blocks, the video side is looking at the audio side, and the audio side is looking back at the video side, constantly exchanging information.
And because they're both latent diffusion transformers, or DITs, hang on, quick refresher. What's a DIT in this context?
Ah, good point. So a DIT is just a transformer architecture, but applied within a diffusion model. Instead of operating directly on, say, pixels or raw audio waves, which is super high-dimensional.
Right. Very computationally heavy.
Exactly. It works on the compressed, latent representation of the data, much more efficient. OVI uses DITs because transformers are great at parallel processing, perfect for this twin setup.
Okay, so identical DITs. That means they speak the same language architecturally.
Precisely. And because of that, they don't need extra layers like complex projection networks just to translate between the modalities or fix alignment issues you'd get with mismatched architectures.
So if I'm getting this right, the video branch uses audio cues, speech, sound effects, to help synchronize itself. And at the same time, the audio branch is looking at the visuals to figure out, okay, what kind of sound should I make and where should it seem to come from?
That's exactly it. This deep, constant back and forth happening across all 30 layers is how they achieve that tight synchronization without needing a separate post-hoc lip sync fixer or anything like that. You can see this structure visually in their figure 1.
It sounds elegant, but okay, the architectures match, but the data itself, audio and video unfold over time differently, don't they? That seems like a major hurdle.
Oh, you've hit the nail on the head. That's the temporal challenge. The DITs are symmetric, yes, but the resolution of the data they process isn't.
How different are we talking?
Well, for a standard 5-second clip in their setup, the video latents break down into 31 tokens, sort of like 31 key moments or frames in the latent space.
Okay, 31 for video.
But the audio, processed through their 1 dVAE at 16 kilohertz, becomes 157 tokens over that same 5 seconds.
Wow, okay, so 31 versus 157? That's roughly a 5-to-1 difference in temporal density. How does the attention mechanism cope with that? How does video token 10 know it should be paying attention to audio token like 50?
This is where I think the real engineering cleverness comes in. They use rotary positional embeddings ROPE for both modalities.
ROPE helps the model understand the position of tokens in a sequence, right?
Exactly. Encodes relative positions. But standard ROPE wouldn't solve the mismatch here. So they introduced scaled ROPE.
Scaled how?
They literally just scale the ROPE frequencies on the audio side. They multiply them by the precise ratio of the token counts, 31 divided by 157.
Which is about 0.197 roughly?
Yeah, around 0.197. That specific scaling factor is like the Rosetta Stone connecting the two temporal viewpoints.
Okay, that's very specific. What does applying that scale do inside the attention layers? How does it help?
Think about it visually. If you didn't scale, when video token 10 looks across at the audio tokens, its natural inclination based on raw rupee might be to look at audio token 10 or 11, but those are way too early in the audio sequence.
Right, because the audio has 5 times as many tokens packed in.
Exactly. The paper shows this in Figure 2. Without scaling, the attention affinity matrix, which shows which tokens attend to which looks smeared diagonally, it's misaligned.
Okay.
But when they apply that scaling factor, 0.197, it effectively compresses the audio's positional encoding timescale relative to the videos. So now, when video token 10 looks across, the audio token with the highest positional affinity is the one corresponding to the correct moment in time.
Ah, I see. So the diagonals in that figure 2 matrix become sharp and aligned.
Right.
It forces the attention to look at the temporally corresponding tokens.
Precisely. And that alignment is what drives the lip sync and the action to sound timing without needing any explicit rules for it.
That is really neat. And beyond the temporal fix, they also streamlined the input, right? The conditioning prompt.
Yes, that's another key piece. Instead of trying to manage separate prompts for video and audio, they use a single frozen T5 text encoder.
Frozen meaning its weights don't change during OVI's training.
Correct. And they feed this T5 encoder a combined prompt. This isn't just a video caption. It includes the caption, a really rich description of the desired audio, and the actual speech transcription if there is dialogue.
Okay, so one big prompt covering everything. I can see how that helps keep the overall semantics coherent.
Definitely. It gives both the audio and video branches a unified target to aim for.
Right. Now let's get into the training. Because a cool architecture is one thing, but making it learn is another. This is where it gets really interesting. You mentioned a 2-stage process, starting with just the audio.
Yes. Stage 1 is what they call OVI-AUD pre-training. They took that audio tower, the 5 billion parameter DDIT, that's identical to the video one.
Which is based on the 1.2.2 video models architecture.
Exactly. They mirrored 1.2.2 specifically because it's a proven high-quality video generator. The idea was, if the audio model has the exact same structure, their latent spaces should mesh much more easily later on.
Makes sense. So they trained this audio-only model.
From scratch, on hundreds of thousands of hours of raw audio data, mostly speech, up to 12 seconds long. The goal was to build a really strong foundational audio model first.
Capable of handling both complex sounds and nuanced speech, like speaker identity, emotion.
Precisely. And they trained it using a flow matching objective.
Flow matching, that's one of the newer diffusion training techniques, right? Often more efficient.
Generally, yes. It focuses on learning the flow from noise to data more directly than traditional denoising score matching. They applied it to the audio latents coming out of a 1D VAE.
And did it work? Was OVI-UAD actually good on its own?
Remarkably so. They show in Table 2 that OVI-UD holds its own against dedicated text-to-audio models like GenAU and even text-to-speech models like Fish Speech. So, yes, the audio foundation was solid.
Okay, solid audio model, solid video model backbone from 1.2.2, both architecturally identical. Now, stage 2, fusion fine-tuning. This seems like the risky part. How do you connect them without messing up the quality they achieved separately?
Yeah, you don't want to break what's already working, so they were very targeted. They froze large parts of the models.
Which parts?
Primarily the feed-forward networks within the transformer blocks. Those often store a lot of the learned domain-specific knowledge.
Okay, so those are frozen.
Yeah.
What did they train?
They only fine-tuned the unimodal self-attention modules, letting each side adjust how it looks at its own sequence, and crucially, the new cross-attention modules that allow the two towers to talk to each other.
Got it. So out of the total 11 billion parameters.
Only about 5.7 billion were actually trainable during this fusion stage. It's about preserving the core representations while teaching the system the new cross-modal synchronization skills.
They used a combined loss function, right?
Okay.
But I noticed the weighting was quite heavily skewed. 85% for the video loss, only 15% for the audio loss.
Lambda equals 0.85, lambda equals 0.15.
That seems counterintuitive if synchronization is the goal. Doesn't that tell the model to prioritize making the video look good, potentially at the expense of tight audio sync.
That's a really sharp observation, and it's a valid concern. But think about the starting point. The video backbone, WAN 2.2, is already highly optimized for visual quality from massive pre-training. It's mature.
Okay.
The audio backbone, OVI AUD, while strong, is the one being adapted to fit the visual timing during fusion. So the heavy video weight, 0.85, ensures that you don't lose that hard-won visual fidelity.
And the smaller audio weight, 0.15, is still enough.
Apparently, yes. It's enough to guide the audio generation towards synchronization, especially when combined with paired sampling, using matched AV clips, and forcing both modalities to use the same diffusion time step. The sync emerges from the joint training, guided by that small audio loss, rather than being forced by an explicit sync objective.
Wow. So they didn't need a separate lip sync loss or anything like that. They just set up the conditions, weighted the priorities, and let the cross-attention learn the natural correspondences.
Exactly. And the proof is, well, quite visible. The aha moment for me was looking at their cross-modal attention visualizations in Figure 3.
Right, the heat maps. What do they show?
Really compelling evidence. They looked at the audio to video attention, basically, where the audio generation process is looking in the video frames, and it lined up perfectly. When generating speech sounds, the attention strongly highlighted the speaker's mouth region. When generating drumming sounds, attention focused right on the drums. Bird chirps, attention localized on the bird's body parts.
So it's not just abstract correlation. The model learned to pinpoint the visual source of the sound it was generating.
Precisely. It confirms that the blockwise fusion is effectively learning these semantic and temporal synchronization cues directly from the data.
And this translates to results people actually prefer.
It seems so. They did human preference studies, shown in Figure 4 using pairwise win rate, or PWR. OVI significantly outperformed baselines like JavaStin and Universe 1.
Across the board, video quality, audio quality, sync.
Yep, clear preference margins on all three client area. People judged the OVI outputs as better overall.
Though they did mention a slight hit to pure video quality compared to the original WAN 2.2 model it was based on, right?
Yes, and that's expected. The WAN 2.2 model was trained on a vast, diverse video dataset. The OVI Fusion fine-tuning used a somewhat narrower dataset of paired audio-video clips.
So specializing for AV sync meant a tiny trade-off in general video generation capability.
A small, understandable trade-off for the huge gains in synchronization and coherent audio quality.
Okay, let's loop back to that combined prompt idea. The ablation study results there were quite fascinating.
They really were, because their first instinct, which seems logical, was to actually separate the text inputs.
How?
They tried using different encoders for different audio types, like maybe use a CLIP encoder for general sounds, T2A text-to-audio, and a T5 encoder just for the speech parts, TTS text-to-speech. Keep things distinct.
Seems reasonable. Did it work?
Not well, apparently. Table 3 shows that this disentangled approach really struggled. The resulting audio quality dropped quite a bit, looking at metrics like inception score and CLAP score. It just didn't sound as good or cohesive.
Huh. So the fix was actually the opposite, merge everything into one prompt for a single T5 encoder. Why did that work better? It feels counterintuitive.
I think the key is that the ultimate job of the twin DDIT system is to generate a single, coherent, audio-visual latent representation. By feeding it one unified prompt describing everything, the visuals, the sounds, the speech, you reinforce that need for coherence.
Ah, so the model can't really succeed at generating one part well if the other part, described in the same prompt, is inconsistent. It forces a joint optimization.
That seems to be the insight. It pushes the whole system to find a solution that satisfies the entire description simultaneously, leading to better overall AV quality and sync.
Okay, wrapping things up then. OVI really does seem like a significant step forward. A simpler yet powerful template for unified AV generation. It definitely raises the bar for open source efforts, moving away from those complex pipelines.
Absolutely. It's a very elegant demonstration of how architectural symmetry and careful temporal alignment can achieve impressive results. But we should also touch on the current limitations.
Right. It's primarily tuned for short clips, isn't it?
Yeah, 5 seconds, 720p resolution, 24 frames per second. That's the current sweet spot.
So generating longer narratives, say minute-long scenes or more, is still an open challenge for this specific approach.
For sure. Future work would need to explore things like causal modeling, maybe generating chunk by chunk and ensuring consistency across chunks, or perhaps adapting the architecture for longer sequences directly.
And the generation speed, 11 billion parameters, is hefty.
It is. Sampling takes time. They mention exploring model distillation techniques, like maybe using something like DMD2 to create smaller, faster versions that retain the quality but generate much quicker. That would be crucial for practical use.
So this whole idea hinges on that architectural symmetry, right? Training an audio model from scratch just to perfectly mirror a pre-existing video model. That itself is a fascinating result.
It really is. It suggests the symmetry itself might be a core principle for effective fusion.
Which leads to a provocative thought for you, our listeners. If true architectural symmetry is so powerful for unified generation, should future foundational AV models even bother with separate pre-training?
Right. Instead of initializing with strong unimodal models like 1, 2.2 and OVI-AUD, should we aim to train massive symmetric AV models completely from scratch, directly on vast amounts of audio-visual data, treating AV as a single, inseparable generative object from the very beginning?
What limitations, what constraints imposed by relying on pre-trained parts might we remove if we took that truly singular from-scratch approach?
Something to think about. You've got the context now.